Let us start. In the last class, we have discussed I-beams like cantilever. We have discussed cantilever beam with addition of that fixed over the top and bottom to ensure it to make to absorb higher amount of load. Let us go through the similar problem here. Sure. Let us go to the similar problem here. Here, we are not having a cantilever beam, but we are having a simply supported beam. But it's also an I-beam, which is given as which is having the dimension of 130 millimeter multiplied by 160 millimeter I-beam millimeter, which means 160 millimeter is the width at the bottom, at the flanges here, and 30 millimeter is the depth at the depth or the height of this I-beam. So it is supposed to be used as a simply supported beam of span 8 millimeter. So here it is a simply supported beam supported from this end to this end, and it is concerned here and here. This is an I-beam with the width of the flange is 160 millimeter given, and depth of the flange is given as 130 millimeter, means 400 here from this flange to this flange, and thickness of the flange is given as around 15 millimeter, means 400 plus 30, 15 plus 15, 30, 430 millimeter, and it is being supported front at this end, and this end is given shown by an arrow. And shown by an arrow, which is and the width, yes, the flanges, what is given here is, I'm repeating again, just the size of the I-beam is 430 millimeter into 160 millimeter, and it is used as a simply supported beam of span width, say 8 millimeter, which is given here 5.92 plus 1.04 and plus 1.04 means that is total 8 millimeter, 8 meter of length. Now, the web thickness is here, it is given as 10 millimeter, means this is the web thickness. This is the web thickness given as 10 millimeter, and flange thickness are of 15 millimeter here. This is 15 concerned here, means this width is of 15 millimeter. Now, the beam carries a uniformly distributed load as shown here from this end to this end of 60 kilonewton over the whole span. Now over the whole span. Now we are supposed to find whether the maximum bending moment is within the permissible limit, is within permissible limit of 180 MPa or not. That is, if not, then the width of the 12 millimeter thick cover plate has to be welded in each flanges from top and or tie the top and both the top and bottom for the section to be set. So also the length over which this plate is supposed to be extended. So first of all, we have to find out whether the concerned load is 60 kilonewton per meter distributed over the whole length is safe for the beam. And because its permissible length is given, permissible limit is given as 180 MPa. And if it is not permissible, not safe, then we are supposed to find the width of a say 12 millimeter thick plate, which is given here. This 12 meter thick, but width is not given. It is covered to both these flanges, either here as well as here, in order to make the flanges strong enough. And we have to find out the length over which the plate is supposed to extend. Either it is to be extended up to the full length 8 meter, or a part of it can be extended to have the required strength, which we are supposed to decide. Now, the strength of the beam is supposed to be maximum 180 MPa. Now, so we are supposed to find whether this maximum bending stress is less than or equal to 180 MPa on width and length of the plate, power plate for safety stress limit. If it is not, this 180 MPa is not the safe stress. So first of all, we have to find out the limiting stress value of the IB. In order to do this one, we have to in order to do the same, we are supposed to find out the moment of inertia of the IB. So first we have to know what is this. We know this is a rectangular shape. So first of all, we have to know the width. Width is given as we are 160 millimeter and height is given as 430 millimeter. if we consider this is a rectangle of 100 millimeter multiplied by 430 millimeter, and this is moment of inertia will be given by 1 by 12. 1 by 12 is base. Base is equal to 100, as it is chosen as 160 millimeter, and height is to be chosen as 430 millimeter divided by 12. And from here, and we have to remove omit this portion of the beam, which is not omit the remaining portion of the beam, which is not as the rectangular shape. If that is this portion as well as this portion. So it will happen 100 millimeter, 160 millimeter minus this flange width means 150 millimeter will be the width, and height will be 160. Will be 430 minus 15 minus 15 means 400 millimeter height. So this is the size of the rectangle whose moment of inertia we are supposed to remove to get the final moment of inertia of the IB. So we are omitting this portion 150 by 400 millimeter cube divided by 12, and this will become 260.1 into 10 to the power 6 millimeter to the power 4, which is used as the moment of inertia of the IB. Now, the bending moment, the maximum bending moment, you know, for this simply supported beam and simply supported band loaded uniformly by a uniformly distributed load of W kilonewton per meter will be given as WL squared divided by 8, where W is the uniformly distributed load intensity multiplied by the total length, where it is given as 60 kilonewton per meter multiplied by total length is given as 8 meter. So W into L 8 squared divided by 8 is the 400 kilonewton per meter, or 480 multiplied by 10 to the power 6 Newton per millimeter. This is the maximum bending moment is possible and which is acting at the middle of the beam. So from the bending moment indication, what you are getting, sigma by y equal to m divided by I, where sigma is the bending stress induced, y is the maximum distance of the furthermost fiber, which is half of the width of the beam, which is 430 millimeter is the with height of the beam divided, is divided by 2, is equal to 215. That is the length of the y from the central axis to one of the section, and it is equal to 480 into 10 to the power 6 Newton per meter as the bending moment divided by the moment of inertia, that is given as 160.1 into 10 to the power 6 into the power 4. Then 160.1 into 10 to the power 6, or this is equal to sigma 196.8 MPa. So the given bending stress with this type, bending stress induced in this type of beam is will be 396 MPa, which is much above that the 130 MPa stress. So we have to design the stress. We have to add the plates on the top and bottom of the bending moment, and we have to find out its width as well as its length, from where it is to be fixed. Either it is fixed for the full length or a portion of the beam can be fixed. We have to calculate first. The maximum moment of the section can withstand. So our permissible bending moment is permissible bending stress is 180. So first we have from the bending equation we are supposed to find out the maximum bending moment the section can withstand. It will given when m sigma divided by y into I. The 180 is the given permissible stress divided by y, the distance of the furthermost fiber of the central axis, that is half of the height of the I-beam, that is 430 divided by 2, 215 multiplied by moment of inertia of the I-beam constant, which is already calculated, 260.1 into the power 6. So this after this equation will reduce to 217.76 multiplied by 10 to the power 6 Newton per millimeter, or 217.76 kilonewton per meter. That is the maximum moment, bending moment this section can withstand. And when the proper plates are fixed, which is the thickness will be 215 plus 12, that is 2 to 7 millimeter, but we don't know the width. The required amount of moment of inertia of the beam to withstand the maximum bending moment will be given as I, and sigma is given as 180, y is given as 227, which is 215 plus the thickness of the width, that is one of the flank, that is 12, 2 to 7, multiplied by the maximum bending moment it can withstand, that is the bending moment we are supposed to withstand, that is 480, that is 480 to the power 6 divided by I, or I is supposed to be 206.3 10 to the power 6 meter. So increase in the bending moment of inertia is supposed to be, increase in moment of inertia is supposed to be 206 10 to the power 6 minus 260.1 into 10 to the power 6, 345.2 into the power 6 millimeter square. It is the required increase in the moment of inertia. Now we are supposed to calculate the width and length of the plate. So what is the width? The B plus if B is the width of the plate, then it's when it is the moment of inertia from the central axis B into 12 is the height given 2 to the power 12 divided by 12 plus B into 12 multiplied by 2 to 1. Means we are first calculating the moment of inertia of the plate, the moment of inertia of the rectangular plate from its bottom face, or that is we are concerning the taking the concern of the width and multiplied by the thickness height, which is the thickness of the plate to the power 3 divided by 12, plus we are adding the moment of inertia of the plate from the central axis of the section, which is given as the area of the plate P into 12. P is the width, the length is thickness is the 12 is the thickness multiplied by the square of the distance, means from the central axis of the I beam, that is 2 to 1 degree. That is given as 2 to 221 square. So it is given as, this is first of all the width multiplied by b to the power cube divided by 12, which is the moment of inertia of the section about this particular line of action about this section. Now we are supposed to calculate the moment of inertia also from this central axis, that is x constant. So you have to do it. You have to add the moment with this moment of inertia, the area of this with plate b into 12 b into 12 millimeter multiplied by the square of the distance, or double moment distance of constant is from it is here from 200 plus 15 millimeter, that is 7.5 200.7 to 21.7.5. To 21.7. 200 plus this is the thickness, plus this is that is 200 is the distance, plus thickness of the flange is given as 15, plus half of the width, that is half of this distance of half of the thickness, that is 6, that is 21. It is 2 to 1 millimeter is the distance of this central axis of this particular central axis of this plate from this central axis of the beam. So that is multiplied by 220 watts square multiplied by the area of this plate P into 12. P multiplied by 12. So thus this becomes the moment of inertia of the beam become this by the both side of the beam, because it is multiplied to 2 from both sides of the center of the section. So this plus this is the b plus 20 b multiplied to 12 into the power 12 to the power 3 divided by 12 plus b into 12 into 2 to 1 square. So that is equal to 345.2 into 10 to the power 6, or b is equal to 294.4 millimeter. So thus we got the plate thickness of the plate, width of the plate, and we have already got the thickness of the plate. Now let x meter be the distance from the support at which the bending moment reach the value 270 kilonewton per kg. X is the distance from the support at which the bending moment is 270 km per inch without cover plate. So what is that? If we take the section here, constant section here, like this, if we take a section, we will make this equation, and the bending equation for the bending moment will be W to L by 2 into X minus Wx squared by 2. So we know the W, we know the length, so we have to put the value of the length here, and X, which is unknown to us, we have to know the maximum bending moment, and that is 16 to 8 by 2 into X minus 6x squared by 2 is 270.76, or X squared is equal to minus 8x plus 800.259. 270, just 1 second. So here we see our I-beam can withstand up to the bending moment of 217.6. So we are calculating the distance of the distance from the support at which the bending moment will reach the 270. So we are putting from this equation, we can have the minus b plus minus square root of b square minus 4ac. B square minus 4ac is minus 21.036 divided by 2, or x is equal to taking the 6.96 meter or 1.2 meter. This length of cover plate, thus the length of cover plate requires 6.96 minus 1.4. So positive sign will take 6.96, or negative sign will take this 1.04. So this cover plate requires 6.94, 5.2 meter, and is fixed at distance 1.0 meter from each end of the support. Let us go for the next problem. Next, the tube of uniform thickness has a section in the shape of rectangular hexagon. As in figure, the tube rests in a horizontal position on two supports that are 2.4 meters apart and carries two loads, each equal to 24 kilonewton between the supports and at equal distances from the ends. Determine the least distance between the loads if the permissible bending stress is 120 MPa. Determine the least distance between the load. So what is given? First of all, it is a rectangular, the constant beam number is a rectangular hollow regular hexagon. First of all, it's a tube, means it is hollow of regular hexagon. So it is of hexagonal shape of uniform and regular thickness, which is given as 5 millimeter. At one side of the hexagon, on major side of the hexagon is given as 80 millimeter. And what else is given? The tube rests on a horizontal position on two supports. This rest is simply supported, and these supports are 2.5 meter apart, and it carries two more bending loads at 24 kilonewton between the supports, but these loads are applied at equal distance from each other, from both the ends. So you have to know what is the least distance between the loads of if the permissible bending moment is, what is the distance between the loads, and if the permissible bending moment is given as 120 MPa. So what is given is shown in the graph. First of all, it is a hexagon. It is the hollow hexagon of uniform thickness equal to 5 millimeter, and of one side of the bigger outer hexagon is equal to 80 millimeter. Next, this beam is being supported at the ends. There is no overhanging position. Both the ends, it is supported at both the ends, and it is carrying a load 24 kilonewton and 24 kilonewton. And this load is applied at equal distance from both this left end and right end. And we are supposed to know the distance between this external applied load. So we have to know first A, and in order to know the distance between 24 kilonewton and 40 kilonewton point loads. Now, first of all, we have to find out the moment of inertia or moment of inertia or section modulus of this our concerned beam. So what is given? It is the calculation of the section modulus is let B is the side of the outer hexagon. So B is given here, side of the hexagon, which is known equal to 80 millimeter. And B inner side of the hexagon, which is not known to us, which are supposed to calculate. From the outer hexagon, what will be the height? H is equal to B sin theta. So it is the height H multiplied by, so if we draw an angle here, and the concern, this is the 60 degree, this is the angle will be 60 degree. and this angle will be 30 degree. So, and this length is outer rectangle is given as 80 millimeter. So the height of this rectangle will be given as b multiplied by sine 60. B multiplied by the angle of this between this base and the hypotenuse, that is b multiplied by sine 60, that is 0.8660 b. So this height is given, we can calculate here. Next, we have to find out the moment of inertia like this. Half b by 2 multiplied by h by 2 into 12. This is the constant portion, and b h cube by 12. Twice b by 2 means half of this length height, means h by 3. B by 2 is the half is here multiplied by this height h, which that is b by 2 to h cube by 12, or plus you have to add it this b by 2 by h cube by 3, and you have to add this the moment of area of the rectangle, the moment of inertia of the rectangle, that is bh cube by 3 into 2. Here by 6 multiplied by, well, this is bh cube by 6 multiplied by 2 is going to be bh cube by 3. Just a second. And x plus x square. Is the triangles here, both this here plus bh cube by 12 is the distance of this thing area. So this becomes 5 bh3 divided by 6 is equal to 0.5. It is becomes 0.543 b to the power 4. So first of all, we have to clear one thing first. We have to draw the IXX. So you have to know the moment of inertia constant about this central line here, not about their individual central line. So first of all, we have to know this first of all, you are supposed to know the moment of inertia about the individual XX line like this, and then we have to add the distance of the full area to the from the distance of this sectional line. So what you have done, and you have to make it 2 twice because both sides are the same. So what you have to do, what this to bh2 is the half of the width multiplied by h cube divided by 12 is half of the width. b by 2 by h cube divided by 12. This is one of the rectangle plus this is another rectangle plus ph cube. Yes, this is the b not b by 2, then plus the ph cube divided by into 3. So that becomes 0.454 p to the power 4. For inner hexagon, we have to find out with a similar fraction, it will be also 0.541 into b small b square, where b we know 8 millimeter, h we know 80 sin millimeter, 80 into 80 sin 60, 80 into 0.866, 69.8 millimeter. So b will be here from this triangle. It is given b minus, that is the, we have to omit this particular height here from here to here, here to here. So this is given as here to here. So the thickness is given as height. This thickness is given as 5 millimeter in the compartment. So this this b, it's to be reduced by. So we are supposed to calculate this portion half into tan 30 degree. tan 30, which is this length, which is to be omitted from the capital B to get the small b to know the length of the inner side. Thus, small b will become b minus 2 into 5 10 to the power 3, 1030 minus 80 into 5.77 is equal to 74.23 millimeter. Thus, for the hollow rectangular tube, Ixx becomes 0.554 b to the power 4 minus b square. We put the value of b to the power capital B to the power 4 minus 74.23 as the small b to the power 4. It becomes 5734 in 573.10 to the power 6 millimeter cube, or Zx is equal to Ixx here by h. This is the height of the h is the distance of the maximum thread. That is the half of the width. That is 69.9, which is the width here, and which is given by the b constant b here. So it is 82.766. 82.766 millimeter. That is the section modulus. Now, how to calculate this distance? Now, from the above loading shown here, that is the distance from each end. So, on each reaction, each end, we have the supports at the each end. So, each will have the reaction equal to 24 kilonewton. As we know, all the externally applied point loads are equal, away equal distance from both the supports. So, support will carry the equal amount of load, that will be 24 kilonewton. Now, maximum bending moment for this case is supposed to be at the center. So, 24 minus multiplied by 2.4, there is a total length equal to 2 minus 24 minus 2.4 by 2 minus a will be the equal equation for maximum for the bending moments. So, this equation will reduce to 24.8 kilonewton, or 24 multiplied by 10 to the power 6 Newton per millimeter. Now, we know maximum bending moment is the bending stress multiplied by the shear modulus. So, we apply bending moment is given as bending moment is given as the stress applicable stress constant is 120 multiplied by 82.766, or A will just become 0.414 meter. So, this distance between these two loads is 2.4 minus 2 into A, that is 2.4, it is 1.572 meter. Here, this problem's main concern is supposed to be to find out the moment of inertia of this rectangular section, which we have calculated by using this particular value of the section, where this is equal to the width and maximum width, where this is the outer width of the hollow hexagonal section and inner width of the hexagonal section. First, we have to find out what is the bending moment of the full beam when there is no, by imagining there is no hole inside. We have to know here. First of all, we have to know this hexagonal portion of the beam, and we have to multiply this portion, not from this here, and here, and this multiply, we have to 2. So we have to develop that into multiplied by 2, and we have to do all this loading by concerning that the triangle here. Say this is one of the triangle, this is one of the rectangle here, and this is another triangle here. So we have to find out this moment of inertia about this base of the triangle, base of the rectangle, again this base of the triangle. Now we know the base angle, base of the rectangle will be base of the rectangle about the moment of inertia of the rectangle about this base is supposed to be the width multiplied by h cube divided by 3, which we have already calculated. Plus, next we have to know the bending moment of this rectangular section above the base, constant base. That is b2, that is bh cube plus bh cube divided by 12. This is the base, constant base itself. Now, here the base constant is equal to this b, that is bh cube divided by 2, plus here the base is here the base is equal to half of this width, because in this case we have to do the cos 60 degree, which is half. If I have in this triangle here, where the angle is here is 60 degree, and this width is b, and this is our height h, and this is our height b here. So from b, this height length will be b multiplied by cos 60 degree. That is b divided by 2. So this is equal to b by 2. That is b by, you have to put b by 2 into h by 3 by 12 here. And this both will be, this is for one triangle, this is for another triangle. And thus this becomes this equation becomes this equation becomes bh cube divided by 12, 3 plus b by 2 into h cube divided by 12, plus another, for another triangle, b by 2 h cube divided by 12. Thus we are getting this equation. Thus we are having this equation in this particular shape, and both are multiplied by 2, as if this, we have the two section here, or here another section is here. And so for the total beam, with this point of inertia, we need to multiply by the full equation, and it will become 0.541 b to the power 4. And in the similar fashion, we have to find out the bending moment of the inner portion of the section. That is the same 0.541 into b to the power 4. And we have to find out the value of b, capital B, which is known to us 80 millimeter, height it is given as 69.28, and small b minus 2.5 to the power 10. That is equal to 80 minus 5.77 into 74.23 millimeter. Thus, by applying this thing, we get the calculation of the bending moment. Then we go for the section modulus. Section modulus here. And do the rest. Now, let us go for the next problem. The figure shows the section of a beam. Determine the ratio of its moment of resistance to bending is in the y plane. Determine the ratio of the moment of resistance to bending in the y plane to that in the x plane. So what we have here, this is one of the cross section, which is mostly rectangular in shape of this 100 millimeter width, as well as height is also not exactly given. Okay. 100 is given as 150 millimeter here. So, and this distance is given as 25 from here, and this is also 25 from here. There's a notch here, notch set item in the section. And we have the section XX from here and section YY from here. And we have to find out the bending stresses or moment of resistances, which is equal to the bending moment for maximum bending moment for maximum amount of stress required for the maximum stress is for XX and Y plane, and we have to make the ratio for the same. So first of all, here also we are supposed to find out the moment of inertia. First, we have to find out moments of inertia in the y plane to that of the x plane. Okay. First, we have to know the section modulus along the x plane. So what will be that? This is the x plane is going on. So we have to find out the bending moment of the fourth section about this x plane. So it will be the moment of inertia of the complete rectangle about xx. So this is the rectangle here. This is the moment of inertia of the total complete rectangle minus moment of inertia of the four triangles about xx. Here, one triangle, one other triangle is here, another triangle is here, another triangle is here. There are four triangles, and we have to eliminate this moment of inertia about these four triangles. Now, Ixx is given as base 12 multiplied by 10 multiplied by this height, cube root of the height, 130 to the power 3, and the angle of the base will be